R over L times time plus that constant, which just e to that constant times e to the negative R over L times time. And so when time is equal to 0 to establish the constant, when time is 0, I'm going to be at my maximum current. I mean, basically, I have this thing set up. If I had, somehow I have this thing set up. I then remove the power supply, so there's still a residual current there, because things don't die instantly, even though we pretend they do sometimes. But the inductor is going to keep that current alive a little bit longer than it would have normally. So if the inductor is not there, the current will die immediately. The inductor makes it live a little bit longer, and so this is just going to be whatever my initial amount of current is, e to the negative R over L times time. In other words, if I plotted it, it's going to die off, as you would expect. And without the inductor, basically be that.
How long does it take to die off? Like a few seconds, like a second?
It really does depend upon this ratio of R over L. That, in general, if you've got negative t over, just call it tau, that's a division. This is known as the time constant. And so in our case right here, the time constant would be L over R. And so the bigger the time constant, the longer it's going to go. Typically, an inductor is in microhenries. So microhenries, and this is generally in ohms. So if this is 1,000 ohms, and this is 0.05 henries, we're not talking a lot of time, but we are talking more than the microsecond that it would take without it.
So how are these things used?
How are inductors used? Again, it's all about controlling the current. So what an inductor does is it prevents rapid change. In high energy physics, they are dealing with incredibly large currents because they're dealing with incredibly heavy magnetic fields, and they create them with the large currents. If there was a power outage and suddenly the current went from 1,000 amps down to 0, that change is so rapid that you would basically create, you basically would create lightning in the lab, because you get this huge change in the electric field, would cause a huge change in the magnetic field, which causes this electromagnetic radiation to go shooting out. What the inductor does is, in case of a power outage, is it would slow that rate of change so that it's much safer. And then it's using this for some reason. I think this is from a computer, but I'm not sure at this point. Or this might be from a TV. Anyway, that's the use that I have more personal experience with. All right, other questions? All right, so inductors in all their glory, or at least some of their glory, but we were last talking about AC currents. And you did a lab on AC current, so let's throw an inductor into an AC situation and see what happens. So I'm going to start out with just the simple circuit of I have an L circuit. So I've got my AC power supply here, hooked to an inductor. It's alternating current, so I've got my voltage across the power supply is equal to some magnitude times the cosine of omega t plus phi. I know that if I am going from this point to this point, that the potential difference would be the same regardless of which path I take. And so my voltage across the inductor would also be equal to epsilon naught cosine omega t plus phi. Which is equal to L over di dt. So let's solve for I. So I have epsilon naught over L cosine of omega t plus phi is equal to di dt. And so my current, that is bad notation there, that should be a lowercase I with a subscript L. I sub L. So I sub L is just going to be the integral of this, epsilon naught over L cosine of omega t plus phi dt. I guess officially integral di. So what is the integral of cosine of omega t plus phi with respect to time? Integral of cosine. It's the integral of cosine.
Sorry.
So I'm going to get a epsilon naught over L sine of omega t plus phi. But I have to somehow deal with the omega. If I took the derivative here, I would end up with an omega on top. And so I need to offset that by throwing an omega onto the bottom here so that when I do the derivative, the omega would cancel out. And that should be equal to the amplitude of the current going across the inductor times sine of omega t plus phi. So my amplitude, so I have IL is equal to epsilon naught over L omega, or epsilon sub naught, which is basically the amplitude of the voltage across the inductor, is equal to I sub L times L omega. So what we end up with is that right there is the inductive reactance. So VL, doing our Ohm's law variation of the amplitudes, is equal to IL times X sub L, where XL is equal to L omega. What we did before was X sub C for the capacitive reactance is 1 over omega C. X of L is omega L or L omega, depending upon how saucy you're feeling. If I plotted them, so when we plot the voltage first, it was a cosine curve, so my voltage across the inductor looks like that. That's my V sub L. And my I sub L that's my I sub L. So as we look at this, you'll notice that we are going to peak in my voltage before we peak in the current. So my voltage across an inductor leads the current by 90 degrees. doing what we did last time with, it's an E and F that we're dealing with here. EMF, if you have difficulty printing, is just an E. So for an inductor, the voltage leads the current. And if you recall, for a capacitor, the current leads the voltage. So Eli, the ice man. Questions to hear? Because we're about to implement this stuff. All right, let's implement. Let's see, the other thing that we had was the C is equal to I C X sub C, where X sub C is 1 over omega C. We know that the voltage across the resistor is equal to I times R. So what we're going to do is take a look at an RLC series circuit. I guess RLC, an AC RLC series circuit. I have my AC power supply, I've got my resistor, I've got my inductor, and I have my capacitor. For an RLC circuit, it doesn't have to be in that order, but it is in series. We're going to solve it two different ways. Way number one, well, you're going to use phasors, which we did last time. So first off, what is the phasor that is common to the most things? If you recall, we have current phasors and voltage phasors. Is there anything that is the same for everything here? Yes. So since my current is common to everything, I'm going to start out with my current phasor. Boom. So that is the current across the resistor, which is the current across the inductor, which is the current across the capacitor, which is the current coming out of the power supply. Now, let's throw some voltage phasors up there. Again, each component has a voltage and a current phasor. So we've got 8 phasors to draw down, that's 4 of them. That just happen to be on top of each other. For a capacitor, or well, we can take any of them. Let's do the easy one. Where is the voltage phasor for the resistor? Where does that fall? Voltage phasor for the resistor. What's the phase difference between the voltage and current phasors for resistors? Go for it, baby.
Phase.
Yeah, they're in phase.
Sorry?
They're phase in the same direction.
Okay, in phase. Did
Yeah.
you pointed it? Oh, sorry, I didn't hear you, BJ.
Yeah.
Just check this.
Now, there are two different scales, one's dealing with amperes, one's dealing with volts. And typically draw the second one shorter. So that is the voltage phasor for the resistor. All right. What about, let's take capacitors, since we did capacitors before we did inductors. Where is the voltage phasor for the capacitor?
Fourth quadrant, 90 degrees.
So down here?
Yeah.
Yeah. Because the current leads the voltage for a capacitor. And where would the phasor be for the inductor?
Wait, we're
For the
turning counterclockwise?
Yeah, they spin counterclockwise,
Right, okay.
because that's what the math people decided long ago, that positive angles go in that direction.
It would also be, no, it's, 90 degrees from VR, or IR in
Right, based on point pencil direction. These are deep 90-degree angles. And for an inductor, the voltage leads. And so this is our phasor diagram. Well, except the fact that we don't have the phasor for the power supply. I know that whatever my potential difference across here is, it has to be the sum of the other three. So I need to add these three red phasors here in order to get the EMF of the power supply. Well, VL and VC are in opposite directions of each other, so I don't know which one's bigger because I didn't give you enough information, but just for the sake of this, I'm just going to assume VL is bigger. So therefore, VL is bigger. This would be VL minus VC. And now I would add that to VR. And so that would be the voltage of the power supply, phasor. So phasor diagram done. But what we really want is the impedance, which I assume we did last time. Well, based upon what I just did, that is a right angle between VR and VL, so I know that I'd use Pythagorean theorem. I know epsilon sub naught squared is equal to VL minus VC squared plus R squared. Oh, try that one again. Back up. Plus VR squared. I need to somehow bring impedance into it, so I'm going to use my Ohm's law bits. I guess the other one that I did not write up here is that epsilon sub naught is equal to the current coming out of the power supply times the impedance. And so this becomes IPS times Z squared plus IL XL minus IC XC squared plus IR times R squared. Now, all of my currents are the same, so they would factor out and cancel. And so what I'm left with is Z squared. Oop, I lost an equal sign there too, equals XL minus XC squared plus R squared. In other words, my impedance for this problem, for my RLC series circuit, is the square root XL minus XC squared plus R squared. Is it your physics textbook that does it? I know one of them does. Ah, yeah. All right, if you look under major concepts, this is chapter 33, major concepts. Number 6 here, they have impedance equals, and then they give you this formula. This formula is valid for that circuit. This is not a generalized rule. These are generalized. This is specific to this situation. I think it's misleading in here. Now, it is quite possible that on a quiz or test, I would give you that formula because that's in the book, and you were to know that this only applies to the RLC series circuit for alternating current. All right, let's do some numbers. Any questions before we do numbers? The RMS for the power supply, or the RMS voltage for the power supply, is 141.421 volts. Let's have a frequency of 50 hertz. And at time is equal to 0, the voltage across the PS is half of the maximum voltage. Equals 0.